we are going to discuss kinetics. And this topic has something to do with speed, velocity, rate. Actually, what's the difference between speed and velocity? One is directional. Which one? Velocity has a direction, exactly. So velocity has a direction, speed doesn't. So velocity, directional. So we can look at how something moves and the direction of it, whereas speed doesn't have a direction. What is velocity? How would you define velocity? A friend of mine once phrased it as, speed is when you can shit in all four corners of a round room. Which didn't help me a lot, but... So what is velocity? What is speed? How would you define it? What is it? We all have a sort of an intuition what we think it is, but what is it? How would you explain velocity to an alien? Oops. Could we, for example, define that velocity might be change in something? For example, in the location per what? Give me an example of a velocity. Give me an example of speed.
Kilometers per hour.
Kilometers per hour. Right, thank God for that. So, change in kilometers, change in location per time. It doesn't have to be kilometers. It can be something else. So usually in biochemistry or biology, we are not measuring anything in kilometers. We're measuring something in concentration per time. Yeah? So millimole per minute. There's usually something that you will hear when we're talking about enzymes. Okay, that's speed and that's velocity. Can a speed be positive? Yes or yes? Yes. Can a speed be negative? Yes? No? No. Speed can't be negative. Speed is always positive, because speed doesn't have any direction. And a negative speed wouldn't make any sense. Velocity, on the other hand, can be negative or positive. Can velocity be zero? Of course it can be. Can speed be zero? Yes, it can. Okay, now here is something. What is a rate? you will very often hear the expression rate. How is a rate defined?
Changing something over time.
Loud?
Changing something over time.
Did you hear that? Shout it.
Changing something over time.
He says, changing something over time. I want you to really shout it because it's wrong.
Okay. Changing something over time.
Changing something over time. Is that correct? Obviously, somebody said no. Why not? It's semi-correct. Sorry?
Changing something over time is velocity, so rate changing something.
So, changing something over velocity, changing something over time is velocity, Lisa says. Yeah, that's right. So it can't be rate. Then, what the heck is rate? Shall I tell you the weirdest definition? Rate is defined as change in something over change in something else. So, miles per hour, marimba. Miles per hour, is it a speed? Speed? Yes. Velocity? Yes. Rate? Yes, because it is a change in distance per change in time. The university has 20,000 students per 3,000 academic staff. Is that a velocity? No. Is it a speed? No. Is it a rate? Yes, it is a rate. Donuts per member of staff. Donuts eaten per day, per member of the staff. That's a rate. So, rate, speed, velocity, in practice, are all put together, but there are slight differences. However, I will use the word rate and velocity very often interchangeable. And rate can also, or also has a direction, like velocity. So rate, direction. Okay, so why on earth am I telling you that? Well, one of the most exciting things that are currently happening in biosciences is that we are getting closer and closer to finding a cure for cancer. And I think that's extremely exciting because at the moment, as it stands, 1 in 3 people will die of cancer. 1, 2, 3. Sorry? You live, they will die. Yeah, but then, yeah. I don't want to go into the maths of it, but if you think about it, cancer can affect anyone. But with kinetics and an understanding of kinetics, we can actually do something about it. How exciting is that? So I want to give you an example of where kinetics can help us. Let's assume we have a cell. And that is that is the cell membrane. In the cell, we produce a receptor for a growth factor. This receptor is transported to the cell membrane and is exposed on the cell membrane. This receptor actually sits there and waits for a ligand to arrive, and then this ligand binds to the receptor something like that. Two receptors with bound ligands will actually undergo a process that is called dimerization. And only when these two dimers are together, they activate each other. So very often, this ligand this receptor phosphorylates the other receptor, and this receptor phosphorylates this. So they do sort of cross-phosphorylation. And only when both are phosphorylated, a signal is passed on to the cell to grow. Or to divide. So that would be in the case of a growth factor. And, of course, we have to have a sort of a switch where we then also degrade this receptor again and turn the whole thing off. That is what happens in a normal cell, what I've just described. And where does kinetic come in, please? Well, kinetic actually regulates this process. So, for example, the delivery of the receptor to the cell membrane very often follows a zero-order reaction. And we will discuss that, exactly what this actually means. The association between the ligand and the receptor here is a second-order reaction. The combination of two receptors with ligands is also a second-order reaction, but of a slightly different type. And the destruction of the receptor-ligand pairs very often is what is called a first-order reaction. Now you can imagine that all these processes need to be finely tuned. Because what could happen if, for example, one of these processes is out of whack with the others? So let's, for example, say that this process here, this one here, is out of sync with the others. Out of sync in this case means like my iPad, because I don't know why I've got such a lag here, but never mind. If, for example, this dimerization is very, very slow, much slower than in a healthy cell, what would be the consequence? If these two receptors don't properly come together, if they're very slow in coming together. What's the effect? What's the effect on this dimer here? Will it form easily? No, it doesn't form easily. What is the consequence on the growth of the cell? Will the cell grow? No, it won't grow. On the other hand, if this dimerization process is very fast, what's the consequence then? Cells will easily grow, right? They are probably growing too fast. What do we call that? It's cancer, exactly. So this is actually how cancer can happen. If, for example, this process here, right at the end, this degradation process, is too slow, so the destruction is too slow, what is the consequence? It increases growth again. Why? Because we have too much of this dimer hanging around, which signals to the cell, grow please. So all these processes need to be really, really carefully synchronized. And I like to compare a cell and the processes in a cell like a very nicely synchronized ballet of substances. And if one of these things gets out of sync with the others, then you have a shite performance, which could lead to disease. So, enough of cancer. Life is depressing enough. Let's try to get a handle on what is kinetics. So I showed you how useful kinetics is in understanding cancer. There's another thing that is quite interesting. We can develop very useful models using concepts from kinetics. One of these concepts is how an infectious disease spreads. For example, flu. How easily does flu spread? Become a pandemic? By understanding how fast it goes, we can do something about it. And people are actually currently developing very, very clever healthcare models. If you have, for example, certain key people who can easily infect others. One of these key people is, for example, me, because I come into contact with a lot of other people, and if I get infected, I can spread my infection. I can spread my germs very easily. Not only because I'm German, yeah, I know that was a bad one, but because I am sort of a hub. But if you take me out, and I don't mean for dinner, if you sort of eliminate me from spreading my germs, we could slow down the rate of how people get infected. So, what actually is a rate in terms of kinetics? Let's assume we have a simple reaction. We have a compound A. And this compound, this reactant, is degraded. And I would like to symbolize it just simply like that. A reactant is converted into something else, whatever this is at that point. We can write for this reaction the rate equals a rate constant and usually the rate constant is abbreviated with K times the concentration of A to the power of M. I'll come back to these things, what they actually mean. And because we are dealing with something that disappears, if something disappears, it's always bad. Yeah? Money. If money disappears, it's bad, it's negative. Because the reactant disappears, we give the whole thing a negative sign. So in this case, the rate of A equals minus K times A to the power of M. This is actually called the general rate equation. And we look at it from the perspective of the reactant, of A. So important things is, if we look at the disappearance of something, we have this negative sign here. That's very important. Now, and we have this rate constant. And we have this thing, this to the power of M. This is actually called the rate order. The rate order of this reaction. Come on. Needs to think about it. Yes, rate order of this reaction. And rate orders, M's, can be any number and the emphasis is on any. It can be a whole number. It can be a fraction. It can be a positive number. It can be a negative number. It can be even 0. So M can be anything. And I think that's quite important. Rate order is just a number. And the general rate equation, this thing here, is only a description of a mathematical description, actually, of what's going on with a reaction. It's only a mathematical description. It has, in fact, nothing to do with the number of atoms or molecules that are reacting with each other. So let me write this out. Rate order, mathematical description. The other thing that tells us how many compounds actually react with each other, this is called molecularity. The molecularity tells us how many components need to interact with each other. And that is a very important difference. Can you have a molecularity of 1? No? Well, for example, if a compound just simply disintegrates, you could imagine that this compound, like a radioactive element, you could imagine that this compound is just a molecularity of 1. So in theory, you can have molecularity of 1. Can you have an order of 1, a rate order of 1? Yeah, very easily. A rate order can be anything. Can you have a molecularity of 2? Yeah? Can you? You probably, most of the reactions that you look at will be of molecularity 2. Rate order 2, possible? Of course it is. Can you have a molecularity of 1.5? 1.5 compounds, 1.5 atoms are reacting with each other. Can you have that? No, you can't. Actually, for molecularity, it can only be a whole number, and it can only be number 1 or 2. Of course, you can say, but. What about when 3 components interact with each other? Well, they need to interact with each other at the same time. That's also in this definition of molecularity. And so far, to my knowledge, there has only been one chemical reaction has been described with a molecularity of 3. 1 out of God knows how many million different chemical reactions. There's only one that has a molecularity of 3. And that's something really exotic. So there's a good chance that you don't have to worry about that. So molecularity is either 1 or 2, Rate order can be anything. So we now can write our general rate equation. Rate equals minus k times a to the power of m. That's our general rate equation. And this delay is driving me totally nuts. I need to investigate what's going on. So very often, as I showed you with the cancer example, we want to figure out actually what kind of rate order we have. How can we do that experimentally? Well, we have something to the power. We have a to the power of this order, and we want this order somehow, this rate order. What do we have to do actually to get rid of a power thing? What's the mathematical? Root? What was the other one? Log? Anything else? I heard something else. No? Root is a nice, would work if it was a 2. Then we could do that. But in general, the best approach is a log. Remember, 10 to the power of something, we log both sides, and we get rid of this 10 to the power. The only problem is that we have here a disgusting negative sign in it. And logs don't work with negative things. Logs are something extremely positive. They are extremely happy logs, because they can only deal with happy things, with positive things. So always remember that. You can't have a log of something negative. So what can we do? Actually, we can use a trick. We can say, instead of a rate, in this case, we use speed. The speed of the reaction. Why would we do that? Get rid of the negative, because speed has no direction. Yeah? So the speed in this case equals k times concentration of A to the power of m. And now we can do something about it. We can take actually both sides log. And in fact, it doesn't matter so much what kind of log we use, as long as we are consistent. Usually people use the log to the basis of 10. But if you are inclined to, you can also use the log to the basis of 3.141598 or something like that. Doesn't make any difference. So what do we get from that? We get log speed equals log k, and the times, according to the rules of logarithm, the times turns into what? Turns into a plus sign. Log k plus m times log a. Does that help us? Actually, it does, because what we have here is the equation for For what? For a straight line, exactly. So I can plot what do I plot on the y-axis? I plot log of the speed of the reaction. And on the x-axis, I plot log of the concentration of A. And I should get a straight line. Something like that. What's this point here? What is this one? What is it? It's C. And in our case, it is log K. What's the gradient? M. The gradient is M, and that is our rate order. So what we can do actually is, in practice, this means we take a concentration, A, of a compound, and check how quickly does this A disappear. How fast react A? So I take concentration A1 and measure the rate 1. Measure concentration A2 and see how quickly this concentration disappears. So that will be my rate 2. And so on and so forth. So I just simply measure it with a stopwatch, for example, and see how fast this reaction makes A disappear. From these data, then, I can figure out what is my rate order. All I need to do is I need to take, how do I do that? I take log A1 and log rate 1, log A2, log rate 2, oops, and I plot them. Get that? Log speed, log A, get my intercept, that is log K, and get my gradient. That's my rate order. Simple as that. That make sense? Yeah? What I want you to do is, if you have already done your write-ups for PCR, not you guys, but if you have done your write-ups for transduction, PCR, and is there anything else? Biological chemistry coursework, hand in? Yeah? If you've done that, please go to the online quizzes, because there is a quiz about finding out the rate order of a reaction. See if you can apply what you just learned today in the lecture. Any questions? God, I'm good. Have a lovely weekend. I know it's only Thursday, but I won't see you before that. Take care.